catch a Murban and I tell them straight across the board, man. Man call Anders.
Hi, and welcome to my new video series called ServiceNow Adventures with Anders. Having adventures in the name has a reason, because the ServiceNow Adventures video series is designed to describe a personal journey of discovery through the technology associated with, or which I think is beneficial to, the ServiceNow platform. I aim to demystify the various components and elements that collectively power this technology. We will kick off the series with a deep dive into a search engine that I've developed, walking you through the learning curve I navigated to get it up and running. Subsequent videos will explore additional topics and tools, all building upon the knowledge and skills acquired along the journey. So, a disclaimer is in place. The short version is that this is my own initiative and that you should probably never do what I do. Well, so, with that out of the way, I want to start out with recording 3 videos in this first journey. The first one is about search engines and my experiences while making a custom one in ServiceNow. The second one will be about the simplest form of machine learning and how Markov chains can be used in the platform. And these two leads to the third one, which is supposed to be about how you can create your own neural networks in ServiceNow, so you can build and utilize your very own AI models. This might change as we move along, but in any case, this is the plan right now. So let's start with talking about search engines. So here's my table of contents for today. I'll start to talk about what is search in the context of search engines, obviously. We'll talk about the index table, which is the core functionality of any search engine. Talk about typo handling. So since people can't really type that well, including myself, we need typo correction or someone to help us to get the right content out of our searches. So performance obviously is important. We don't want the search to be slow or people won't be using it. And have a small look at search in ServiceNow, because I want to point back to the old Zing search engine and see what it could do and why it was necessary to move from that one to AI search. And last, want to have a demo and have a look at the search engine I made as a result of my research and trying out different things. So a little bit about myself. My name is Anders and I am a certified master architect. I'm currently working at KPMG in Norway, only with ServiceNow as an architect. And I'm also a ServiceNow MVP, so shout out to the developer advocate team in ServiceNow and everybody's there. You're the best. And yeah, so let's start with what is a search. So a search is, as everybody understands, is looking for something, right? So, but in a search engine, it means creating an index of what you want searchable and to make it available for the end user to find what they're looking for. The user interface in a search engine is the search field with the search results. The search engine goal is to take the search input and to return matches in content. There are several established methods of database search. So, and that brings us to the index table. So indexing is the core functionality of a search engine. If you have ever used a cookbook, you'll be very familiar with the index pages. It's pages where you find the dish you want to read about, and it will tell you which pages to turn to read that part of the book. In search engines, indexes work exactly the same way. Index tables store the searchable words themselves, and this is where you go to look for your content. Those index words are again pointing to where the articles or catalog items are in your instance. The reason for having an index is to improve performance and speed. Imagining browsing through an entire book for all the words you want to read about, and you will easily understand the use of an index. At the same time, too big index will make performance bad as well. ServiceNow has many index tables, and by tweaking around with the ACLs a little bit, you will be able to open them up and have a look. So I believe they're called TS_index, if I'm not wrong, but you'll just see a list of words and they'll have some references to other tables. So in my example later, I have made my own custom index to understand how that worked. So we'll look at that while we move along. So you'll have all the words that you want searchable in the index. So you don't put all the words possible, only the ones you want searchable. And you give the word a score or a weight for each target, meaning you have maybe the word laptop that could be in 20 articles, but maybe it's more relevant for one of them than the other. So you need a score to show the search results. This one has a higher priority or is more important than the other ones. We'll also look at how that works and how you can set your own scoring or weight points for a word against an article. And then with the search engine search field, you only query the index table. So you don't query the articles themselves, but the index table will point to the articles later. So by limiting the size of the index table, you get a more efficient, more accurate and faster search. So you want to remove words that aren't relevant. So verbs usually aren't that relevant, and words that occur in every single article, you want those not searchable, because searching for the verbs will return all of the articles, and that doesn't make any sense. So using stop words is basically a word that is removed from the index. So you have a list of words and say these aren't relevant for me. You can have a dynamic stop word functionality saying that I'll count through all my words, and if I see that this word occurs in all of the articles, I'll just remove it. But as this is a bit consuming on the resources, you might want to use just a pre-generated list for it. So that is what ServiceNow does. And actually Google used to have a list of less than 20 stop words, but over time increased to many more. It's hard to tell exactly how many. Now Google has changed their algorithm to not use stop words at all for index removal, but it's now part of a very complex system. Now there's one example that shows the good use of stop words. So if you search for the President of the United States, and then you search for my president and the United States, the context is very different. So before, the stop words would remove the, of, and my, and in these ones. And the only relevant search words would be president and United States. So you would get the same results. That is why Google decided to step away from using stop words and do something else. However, using ServiceNow, it doesn't really matter. The search, the word corpus, the amount of articles is not nearly as much as Google needs to worry about. So using stop words is actually a good thing. So this is why the search engines are using it. You have access to the table already, and if you're making your own search engine, obviously use stop words as well. Performance. So let's look at this. So this is 3 ways of searching through data structures. So you have 3 different data structures. The first one is an array. So array search is an array is a list of words. So it's linear and you have all the words lined up in a list. So if you want to search through an array, you'll have a for or a while loop, and you'll just look for it. Next word, is that the one? Is this the one? And just move on. And it potentially is the first one, and it's very fast, but it could be the last one. It takes forever. So the larger the list, the longer it takes. So this is called an O. It's called a big O notation. So in computer science, big O notation is used to classify algorithms according to how the runtime or space requirements grow as the input size grows. Meaning, in this case, if the array gets bigger, the potential search time increases with the size. So since this is linear, if you double the length, it potentially takes twice as long. is what it means. So that is not a very efficient way of searching in computer science. So then you have the binary search tree, which is a very efficient way of searching. So imagine you have this tree. This is one word per node, and if it's say a dictionary in alphabetical order, you will start in the middle, and you take everything which is alphabetically before this one to the left side, and everything on the which is on the right side you take here. So then you can start in the middle and say, so my word, is it after in the dictionary alphabetically or before? If after, go to the right. So as soon as you make one jump, compared to one jump in the array, now you have eliminated half of your tree if it's a balanced tree. And from 1,000 words, let's say it's 1,000, now you have only 500 you have to search through. And the next jump, you do the same thing. Now it's only 250, and so on. So with a binary search tree, you have like 7, 8, maybe 9, jumps, and you have your result. That is very efficient. You can imagine that is like having an array with only 10 elements in it, and searching through that is just very fast. This third one is called a hash set. So you can compare that to having an object, and the object has a parameter. So the object has the parameter name, and the value is the name, or you have the parameter age, and you have the value age. So if you go directly to the parameter and say, give me the value of the object's name, it will just give you that. It doesn't really search, it just goes straight to the value and brings it out. So that is a constant time. So same time regardless of search. So even if the size of the object gets bigger, since you're going directly on the parameter level, you'll get the result immediately. But it requires that keys are unique, right? So why doesn't search engines just use this? Well, the reason is that it doesn't really care about if you're making a typo, for example. So that's an issue, right? So if you want extra functionality like typo handling, you cannot really use a hash set, because it's only unique values, and unless you want parameters that covers all potential typos, which you obviously don't want to do, and hash sets isn't the way to go in search engines. We do come back to binary search trees. The issue with binary search trees is that the simplest form of it anyways, the way I explain it doesn't really take into consideration if you made a typo either. So let's say you start in the middle, let's say you start on the character N, and the typo is the first character, so it goes to the right to look for it, but in reality it's to the left. So you eliminate finding the possibility of finding your word because of the typo. So there's luckily someone thought about this already, so they made a version of the binary search tree called the BK tree, and it's a binary tree like this, but it's structured not by alphabetical order. It's structured in a way that looks for the distance between the words. So remember I talked about the Levenshtein distance algorithm, looking for the distance between words. So you use that one to say, well, we start with this word, and if you're looking for something, it looks for the distance of the words, if it's less than something or larger than something, and it finds it in the case of looking for distance. And when it doesn't, if it finds the distance being 0, then you found the word. But if the distance fluctuates, going down to close to 0 and goes back up, then the ones closest to 0 is most likely the word. Or you can make a threshold saying if the distance was just 1, then maybe it was a typo, or if it's 5, then it's not here, you can't find it anymore. So that brings us actually to fuzzy search. So how that works. Fuzzy search is another way of saying typo handling. So if we look at this one, at the distance, I said if the distance is 1, then what that means is that if you make one insertion, like in this example, cot to coat, that is one insertion, that we insert an A, that is a distance of 1. If it was from cot to coats, the plural form, then the distance would be 2, because you need to insert 2 characters. You can delete and you can substitute, or you can have transposition, as in swapping the position of 2 characters. That is different ways of making changes to one word to compare to another one, and the distance will be anything from 0, which is the word is similar, or anything more than that. And the way you do it is that you make a threshold. Let's say that 1 or 2, then it's probably a typo. But if it's more, let's consider it the word isn't there, that you can't find it. This is a different word. So if you compare 2 words and the difference in distance is 3 or more, maybe it's another word. So I do have a demo I'd like to show. Let's see if I can jump over to my instance here. Okay, so this function here is called, well, it's a function that's based on the Levenshtein distance metric algorithm. So this is the algorithm based or placed in a function, and if you Google it, you'll find it. So you can just take it and use it for yourself. So what this does is it looks for deletions, insertions, or substitutions, and it tries out these different ones and sees what it takes to make a match. So in this case, I have 2 words I want to make a comparison for: ServiceWow and ServiceNow. So it's a very simple thing, because we know the distance is 1. So if we substitute the W here with an N, it would match. So if I run this one, you can see that the distance is returned as 1, right? But if we add some more, let's say we add 22, run it, the distance is now 3, because it would have to remove these 2 in addition of changing this W. And if I so it's lacking a W, that is the distance of 1. And if we write something else, laptop, you can see the distance is quite large, so it's 9. That is obviously not a typo anymore. So that is how search engines find typos and can correct them. So it's looking through the word, and if it doesn't find it, it will try to look for the one with the lowest distance value. So later you'll see that I'm using this in my search engine, and it's functioning very well actually. So let's go back to the slides. Oops. There we go. Okay, so relevancy, very important. So if you have words in your search engine that points to different articles, you need to figure out which of these articles are more relevant than the other ones. That is very difficult. So you have this algorithm called TF-IDF, an information retrieval technique that weighs a term frequency TF, and its inverse document frequency IDF. So the TF-IDF algorithm is used to weigh a keyword in any content and assign importance to that keyword based on the number of times it appears in the document, if that makes sense. So let's say you have the cookbook again. You're searching for the best chocolate cake recipe in your cookbook, and a recipe that mentions chocolate and cake many times might get a score. But if these words are also in lots of other recipes, their value might go down a bit. However, if the recipe also includes the word best, which might be more rare, it could get a boost in the rankings. Finally, if the recipe is very short and still includes all your search words, it might get a higher score than a longer recipe with the same words. So that is what this TF-IDF algorithm will take care of. It will look for example, I'll give an example. Let's say you have a 100-word long document and it contains the term cat 12 times. Then the TF, the term frequency of that is 12 over 100, so 0.12, right? But the IDF is how many documents totally does the word cat appear in. Maybe it's in 10 documents. And then you take that you take the 10 documents and you divide it by let's see, my notes kind of making me crazy to look at this. So okay, so you do the logarithmic of 10 over 1. Sorry, it's math, I'm very bad at it. So the answer is 1 for that. So if it's in 10 documents, then the value is 1. And remember the TF was 0.12, and you times 1 times the TDF. So the weight is 0.12 for this one, and you'll get different values for different words for each article. So the word, let's say the word is laptop. The word laptop might have one weight, TF-IDF for one article, but different value for another one. And that is how you can see that looking for this word might push this article on top and this one a little bit down. So when you're looking for several words, you just add these together and you get you say, okay, so for this article the total value is this for all these words, and for this other article the total value is something else, because you have the values for that word and you add them up and you get your order basically. Right. Sorry, it's a bit difficult to explain math when you didn't really go to school, right? So then you have the BM25. So to explain, BM25 is basically a version of the TF-IDF, which, because the simplest form of TF-IDF didn't really take into consideration that some articles might be very small and some might be very, very long, like a book long. And the weighting was, so the curve was too steep. So what BM25 is just a version of it that sort of levels out this curve a little bit, that takes into consideration that some articles or some material is much larger than other things. So it will work better, and it's basically just a little tweak in the algorithm that makes this work. So I believe by personal research that ServiceNow is using BM25. I can't say for sure, but I know that I'm using it for my search engine. So the relevancy is this. So it makes the score for the words per article or catalog item or whatever you're searching for. And then you have the stemming. So stemming and synonyms will help you reduce the index and thereby making things more relevant. So the problem is that if you have a word like, for example, connect. Actually, I have a slide on this. Where is it? Not there. Okay, so we'll look at this one. So the stemming, let's say you have the word connect, or the words connecting, connected, connection. It's the same word really, with sort of different meaning, but it's the same word. The stem of the word is the same. So what you want to do to reduce the index size, and thereby by having, so someone might just say connect, they'll have some articles connected, they get other articles. You want to have only the stem word registered in your index. So, and thereby when people are searching for connected or connect or connection or connecting, you translate, you don't have to show them, but you basically translate their word to the stem and you look for the stem in the index. Was a guy named Martin F. Porter who made an algorithm to stem a word. It's partly static, so it's just saying remove, plural form, remove tion for connection, ing, remove that. So it has some static things for English language, and it sort of removes this. And there's people who's using this and translating it to their own languages, but you can't really stem something in other languages without having knowledge of that one. So Martin F. Porter made something called the Porter stemmer algorithm, which does this. So I do have, let's see if I can find it. Porter stemmer example. So we're going to go back to my instance here. Let's remove this. Yeah. So I have found online the Porter stemmer algorithm. You can Google it and you'll find it too. So I'm not going to show you. It's just a long list of suffixes that it removes, and some plural forms and some vowels that it removes, and so on, and combinations. So you don't need to see that. So let's just see what it does in case of the result. So let's say the word is documentation, and I'm going to pass that into the Porter stemmer, and we'll see what happens. So if I send this one in, it says here the stem of documentation is document, right? And even if I say documents, it will also say that stem is document. So you can do this with lots of things like internationalize. And it doesn't make sense, but it's actually internation, because that is the core word of internationalize. It doesn't need to make sense to you like a language, but it does make sense in a computer algorithm, right? So I would, in this case, if I found this word and I want to index it, I would basically index this, only this part. And if someone is searching for international, I would actually not search for that. I would search for something else. And in this case, actually, it created a new one. So international has a different stem than internationalize, which is kind of weird, but that's just how it works. So in this case, I'll have two sort of similar words in my index, and I would have to evaluate if I want that to be the case or not. In my search engine, I kept the algorithm as it is, and it works quite fine. So we'll have a look at that in a second. Right, so going back to this. So search in ServiceNow. So now the ones being used in ServiceNow is currently called AI search. It always kind of bothered me, the name, because it really didn't have AI in it, and that's just how I coined the term. AI is way more than what AI search could do. So AI search to me is a bunch of very clever algorithms that helps you search and find new things. And that's fine, and everybody should use AI search, and I do too. Nobody should ever make their own search engine, and everything I do is wrong. But anyways, before AI search, you had Zing search, which was, and I think everybody agrees, a quick hack to make something searchable. So it looked through tables for your words, and it took a long time. To change anything in the search, you had to basically go into code and change what it looks for. And it looked through things with glide records and, very crude searches. It also had the same scoring system that I just talked about, and it used stop words, stemming, and synonyms for their index tables, which is great. So that worked back then, even though it was slow, and it works still. It used type ahead search, which is still my favorite functionality in the search engine. So you write something, and immediately while you're typing, you get the results. The problem with type ahead search is that while you were typing and you stopped, and it had a timer on saying, "Oh, we stopped, I'm gonna search now," and it made a call to the server, and it gave the results back. So if you're typing slowly or thinking, it makes server calls back and forth. So with a large instance with many users, the server calls to the client side back and forth would take a load on the system, and it's not very practical. So actually, if you go now to AI search, you will see that the default solution is something called suggestions, which is just looking like if you make a search in AI search, like you're looking for reset my password, then it would actually store that search in a table for reuse later, for reuse as a suggestion. So next time I or someone else comes in and types reset, and it's quickly finding, oh, someone searched for reset my password, that might be it. So it just say, oh, here's some suggestions for you. Reset my password, right? And there's a scheduled job running once every night that looks through these search queries and moving them to the suggestions table, which is what you see when you're typing in AI search. The problem with suggestions is that if you have an employee that suddenly hates his life, he will go in there and search for the stupidest stuff ever, like reset my job, reset my life. And if it does that enough times and nobody notices, then one day you'll try to reset your password and you'll get that. If you think that is absurd, this has happened with Bing search, for example. You had the craziest suggestions in search engines before, so they're much better now in sort of filtering those out. I'm pretty sure AI solutions has something to do with that now, but it's why I'm not a fan of suggestions in ServiceNow, because it basically just throws out whatever someone else wrote many times. Anyways, type ahead search was great because it found your solutions while you were typing, and it is also something I made for my my search engine. The consistency of the search is great because it's used throughout the platform, not only on the portal side. So that is a benefit of using these out-of-the-box search engines, that you can have a search through specific search sources like an article or catalog items, but you can also go inside the platform as a case handler and search through tickets and whatever you want. And as you can see, as of Quebec release, AI search was live, and it included fuzzy search, which was not a function in the Zing engine. So that leads us to my AF search, which is my working title, not AI search, but AF, which AF being my initials. And I want to show you the result of everything I said. So I've talked about the index table. I made my own custom one, being much more compact and much smaller than the ones that ServiceNow has, because I don't really need everything searchable. I just need to, in my case, I wanted articles and catalog items, nothing else. So I just indexed that. And I decided to move the index to client side, meaning if you have the index client side, you don't need to make any server calls at all. So making server calls takes time. You have to wait a second or two and then you'll get your results. But if you have a client side, it's pretty much zero latency. You get the results immediately. And I know what you're thinking. But that's not a good idea. The file will be too large, something like that. Well, no, not really. So I'll explain. So in my search engine, there's type ahead search only because this is possible when the index is client side. And the goal was speed. So I wanted the searches to be immediate. So the concern about the size of the index and how stupid it would be to download that client side, I'll address after I've shown you the search engine. So let's go back to the instance and have a look. So this is the simple proof of concept search engine of AF search 1.0. So let me just say immediately, if you look at the background picture, the size of this picture is actually larger than my index file. So I think this is like 400 kilobytes size. Nobody cares, right? If that's the size of the background picture. Now my index file is slightly smaller than that. I think 350 kilobytes or something like that. It does change a little bit as I remove or add articles while I'm testing, but it's not really big. So unload on this page loads the index and nobody notices, basically. So if I'm going to look for, I don't know, phishing, notice that I'm trying to mistype as much as possible and just seeing how badly I can type before it comes up with a result. Scam, avoid. Right. So as you can see, if you didn't see that, go back a step and look again how quickly it found the typos and how quickly the results came in. So I'll copy this and just paste it so you see that it's immediate. So I'm gonna paste it now. Boom. So you didn't even notice. Zero latency. It corrected my typos and it found the search results both in articles and in catalog items. Right. ServiceNow. See, I didn't even bother to type it correctly. It found it, right? And now it looks wrong, but this article actually has ServiceNow in it, so that's why it shows up. Let's do reset my password. 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 And actually that's actually one of the cool things about making a custom solution, that you can make your own additional functionality. So I wanted to say that if I found an exact match, I want to put out this like a checkbox. I guess the same thing that ServiceNow has, which is genius results, right? So it does say, oh, this is a car that's more likely a call to action. This is what you want. You click here and it goes straight to your thing. So I wanted to make the same thing here, right? The values here, let's go to computer. Yeah, so the values behind here is just me visualizing the weight score, so the TF-IDF score. And as you can see, I'm just ordering by the larger number and going down, and I have a limit for 5 just for my proof of concept. But I assure you, if the limit was 10 or 20, it wouldn't matter. It would be equally fast because the index is client side. So is the index record, which is a JSON file, 350 kilobytes? Not really, it's much larger. But for me to make this work, I needed to understand compression, which is something that I think is very crucial in working with larger data sets. So I want to talk a little bit about this, because it brings me back to why this is a series of videos which will progress, and it's a journey, which is why this is ServiceNow Adventures, and it could be ServiceNow Journeys. You know, the thing is that by adding compression, so I compress the data, I load that one, and I decompress it. Decompressing is very fast, so I'll use something called the LZ compression algorithm, which you can Google, you'll find it. It's very fast to compress and decompress it, so that doesn't take much time at all. So you end up with being able to do these stupid things, but it kind of works anyways, right? Now, again, disclaimer, you should never do this. Nobody should do it, but it doesn't matter. I didn't make the search engine for you to use it, or for me to use it, or for anyone really to use it, but to understand search engines and to learn something. And by making this search engine, I learned about compression. I learned about stemming. I learned about, weighting algorithms, TF-IDF and BM25. I learned about distance metrics, so how to find the distance between two words. This is very important. And very importantly, I learned about binary search trees and how you can use different versions of binary search trees. And why this is important and why this is a journey is that now not only do I have an understanding of the search engine, but I also have tools to make other stuff now. So in my next video, I'm going to talk about Markov chains, which is basically a machine learning algorithm and a data structure, which is one of the first, I would say, that has some practical application to it. I'll use this one to make predictive intelligence, right? So by a very little code, you can make predictive intelligence, meaning you insert a short description, and it says, oh, that should be assigned to IT or HR or whatever, based on statistical data. So the data that you already have in your platform. We'll get back to it. I don't want to leave out too much now or tell you too much now. But what I learned when I made this again led me to learn about how AI works and neural networks. That will be my third video. So how does AI work? How does neural networks actually work? And can you make it yourself? The answer is yes. And can you make practical applications in ServiceNow to make even make functionality which is there, or make functionality which isn't there, right? So that, I guess, is the point of starting with the search engine, because all of these elements that I've talked about, they sort of move over to the next part of the journey, and that part of the journey brings into elements that helps me understand the next part again. And that is what I want to express and explain to everybody else. I want to communicate that by experimenting and just trying things out, even if the search engine was a failure, all of these things I learned along the way is valuable, and I can use it later. And yeah, so that's, I guess, a wrap. I want to thank you for attending my little video, and I hope I see you in the next ones. So I'll try to keep it a little, I guess, having some music in the background, maybe bringing some people, have some unscripted talks. The point is to learn things and to share knowledge and to see how we can move forward in our lives and be great people in the ServiceNow community, and to learn and teach other people. So by that, thank you for attending, and I'll see you next time.